we're on some chapter. 14 sounds like a winner. Let's go with that one. Chapter 14 it is. And in chapter 14, we were talking about acids and bases in this chapter. And we got into all the fun formulas about the pH and all that good stuff. So a reminder, we had a number of formulas here. We had our Kw, which is the equilibrium constant for water, which is the concentration of H plus times the concentration of OH minus is 1 times 10 to the minus 14. Remember again, as we talked about, pretty much H plus and H3O plus are pretty much the same deal here. So anywhere in formulas or equations, you could really swap both of those things out for each other. We could use this to solve for either the H plus or the OH minus concentration. And it's really the same calculation as 1 times 10 to the minus 14 divided by either the H plus or the OH minus, depending on what you were given. And we could compare those two. And if the H plus concentration is larger than the OH minus concentration, that means pretty much you have more acid than base in that solution. Then it's going to be acidic. If the H plus equals the OH minus concentration, they both will have a value of 1 times 10 to the minus 7, which is a neutral solution. And if the H plus is less than the OH minus, which means obviously that we have more of the base part of the solution, hydroxide floating around that solution, then it will be basic in this case. A couple of reminders that when you're comparing these two, you do want to make sure you take into account that the exponents are probably going to be negative, so that the smaller negative exponent is the larger number, right, when you're comparing those two. We then got into the talk of the pH scale, which runs from 0 to 7 to 14. Below 7 there is acidic. Above 7 is basic. And our 7 there is neutral. And that is because of this right here. So again, because they are equal to each other, they will have that concentration of 1 times 10 to the minus 7, which really does give you a pH of 7. So we'll go with 7 as neutral. And again, if it's basically 7 with some rounding, then it will still be sort of considered neutral. But, you know, if it's like 7.1, then it's slightly acidic. And again, if it's, you know, less than that, it will be slightly 7.1, slightly basic. If it's less than that, it'll be slightly acidic. The relationship, right, is as the H plus concentration goes up, the OH minus concentration goes down. So they run opposites of each other. To calculate the pH, it is negative of the log of the H plus concentration. And we also talked about calculators here as well. And that is if you have a display calculator, again, you punch this in exactly how the formula is written. If you have a non-display calculator, again, you have to kind of work backwards with these formulas here. We saw a similar scale that measures POH, or the OH minus concentration, which is the POH, and that is minus the log of the OH minus concentration. The pH plus the POH equals 14. So that does give you a little bit of variety as to how you could solve some of these things, depending on what's given to you. So again, if you're given like the OH minus, you want the pH, you can get the POH, subtract 14, and you got the pH at that point. We also saw that if you have the pH given to you, from that directly you can calculate the H plus concentration, and that is equal to the inverse log of the negative pH. Once again, on your calculator to do that, that usually will pop up a 10 and a caret, and that's usually like the shift or second button and your log button to do that move right there. And same thing with the POH. If you have the POH given to you, you can get the OH minus concentration from it, and that would be the inverse log of the minus POH. Who didn't miss? Anyway, everybody get the roll sheet? Yeah. I'm proud of you for figuring that out. That deserves a hand right there. I think. That's did it miss you? Oh, it always miss you. We got you. That's good. We're good. We're still good. It's only 6 weeks in. That's all right. We're good. We got it. All right. So we we got the OH minus concentrations, the inverse log of the minus POH. So you do have a number of ways to sort of solve these problems depending on which route you take. A reminder that when you are asked again if it's acidic, basic, or neutral, it should only be one answer. And again, that very commonly comes up. People give two answers because they calculate both of these guys and they give both answers based on that. So my recommendation, as we talked about at the end, is you should probably always look at the pH, as that is the scale most people have in their head. Once again, the POH scale actually runs opposite of the pH scale. So less than 7 is basic on the POH. Above 7 there is acidic. So there are opposites of each other. So since most people have this scale in their head, that is probably the one that you should look at to determine it. Now, any questions on any of that stuff there we talked about last time? We also talked about sig figs with pH, right? So number of decimal places in the significant number of decimal places in the pH value is equal to the significant figures in the concentration.
The pH and pH are inverse.
They are, as one goes up, one goes down. Yep. And that's why their scales basically run opposite of each other, right? So if you have a high pH, you'll have a low POH and vice versa, obviously, in that case, yeah. Other questions? Okay. So I think this is where we left off. So I think we have this one to go. So why don't you do that one? One last root here, pH, POH, OH minus. Is it acidic, basic, neutral? We'll add that to the list here. Yeah, so again, as you said, there's multiple ways you can kind of approach this. In this case, we do have the H plus concentration given to us, which means we could use KW to get the OH minus if you wanted to first. You could also just get the pH there from it. So in this case, I'm going to just get the pH first. So again, you could go either way. pH is equal to minus the log of our H plus concentration, which is 3.5 times 10 to the minus 6. And that's going to give me a pH of 5.46 in this case. Again, now that I have the pH, it's pretty simple to get the OH minus or POH from it by just subtracting 14, as the pH plus the POH is equal to 14. That means that our POH here would be 14 minus the pH of 5.46. And there will give me an 854, I think, there as our POH. At this point, you still have a couple of options. You can go back to KW to get the OH minus, or you can use the inverse log of our POH now that we have it. So I'll do that one. The OH minus will equal the inverse log of the minus POH. So again, on your calculator, it should probably look something like this. Do not forget the negative sign there. And that's going to get us here, negative 8.54 in this case. And that will get us something like 2.9 times 10 to the minus 9 molar, or a bunch of threes at the end of your, or a 3 with a bunch of zeros at the end of your calculator. Again, on my calculator, I had all zeros and a 3 before I put it in scientific notation. So if you had that, we will take 3 as well. Now, any questions on any of that there? This would then be acidic, basic, or neutral. This should be acidic, again, based off of the pH. Yeah.
Because I just did it backwards. I got
It should. So like I said, if you took the KW route, you would get the OH minus concentration, and then you have each of those, you could get the pH and POH. Should give you the same. So whichever sort of way you want to go should work. You might eventually get maybe something slightly different if you, depending if you did a little bit of rounding or something like that. But you know, in the most cases, it should give you pretty much the same answer. By the way. Yeah. Other questions on that? Questions on pH, POH, H plus, OH minus. Obviously, you need to be able to calculate all those things. All right, then let's talk a little bit about acids and some different types of acids. So first off, strong electrolytes, if you remember maybe from 50, electrolytes are substances that go for a swim, right? And they break off into ions, and those ions can conduct electricity. There are strong electrolytes which 100% break apart. There's weak electrolytes which mainly stay together but break apart a little bit into ions, still able to conduct electricity. So you see the light bulb shine dimly as opposed to very brightly in a strong electrolyte. And there's also non-electrolytes, which basically dissolve but do not create ions, so they do not conduct electricities. So acids and bases are electrolytes, strong electrolytes and weak electrolytes. So something like sodium chloride here, which is a strong electrolyte, in solution, you have basically 100% of those ions floating around. Now, something like acetic acid, which is this guy right here, that's acetic acid, and that breaks apart into acetate and H plus. And this is a weak acid, actually. And we know this is a weak electrolyte and a weak acid because we see the arrows heading in both directions. So that's, again, a reversible reaction, and that typically occurs with weak electrolytes. That means in solution, you actually mainly have this guy still there, but you have a little bit of these guys that have been developed. So that's why it's a weak electrolyte. Now, strong acids are strong electrolytes. So in this case, we do have water in the equation, which means in each of these cases, our H plus is going to donate the water over there. Our acid is going to donate it, and that will give us our H3O plus. And in this case, Cl minus. This will give us H3O plus and NO3 minus. So we give us H3O plus and ClO4 minus and H3O plus and a little HSO4 minus in this case, right? So a list of some strong acids. This is a good list, but you should know these strong acids. So pretty much everybody here that's listed, our hydrochloric acid, our nitric acid, our perchloric acid is a strong acid, also sulfuric acid, hydrobromic acid, hydroiodic acid. These are all strong acids. So I would say, you know, if it's not one of these six, it's probably a fairly good shot it's going to be a weak acid. So these are kind of your six major strong acids. And again, when you have each of these guys in solution, they will 100% break apart. So again, if you have something like HCl, which is a strong acid and strong electrolyte, in solution, you have 100% H plus and Cl minus ions floating around. This again is another way you can write this equation without the water, showing basically the acid breaking apart. It's a strong acid because you have 100% of that, which means in this solution, you have a fairly good amount of H plus basically floating around because it all just basically breaks apart. And that's what makes it obviously a strong acid, as opposed to something like acetic acid here. In that solution, you have a lot of acetic acid still together, and you got a little less amount of free H plus floating around. So again, still able to produce some H plus in that solution, which is why I still consider an acid, but nowhere to the extent that hydrochloric acid can produce in terms of the H plus. Any questions on that there? Now, weak acids we just saw there, like our acetic acid. Hydrofluoric acid is another weak acid, and again, in each of these cases, our acid is going to give away its H plus, and that will give us H3O plus, and in this case, F minus. Got H3O plus and NO2 minus. Well, H3O plus and SO4 2 minus, and a little H3O plus and some hydroxide in this case, actually. So each of these are some weak acids, and those are very common ones: hydrofluoric, nitrous, also acetic acid is a very common weak acid we come across a lot. Things like HCN is also a weak acid. So you'll get familiar with some of those. But again, the best way probably is there will be a lot of information sometimes, and the problem will help you decide if it is a weak acid or not. And also, again, just kind of knowing those six strong acids, if it's not one of those, then it's probably going to be. Now, strong bases are also strong electrolytes, which means they will 100% break apart in solution. And a lot of our strong bases will have hydroxide in it. And a lot of strong bases come from group 1 and group 2 on the periodic table. You know, you got your lithium, your sodium, your potassium, your calcium, strontium, your barium. You know, if you kind of take this way, and this way, put those guys with some hydroxide, you got some strong bases. So those are a lot of the strong bases. That's why they're called the alkali metals, alkaline earth metals. As we might have mentioned before, alkaline pretty much means basic. So a lot of our really strong bases do have hydroxide in them and come from group 1 and 2 on the periodic table. Not all bases need to have hydroxide as part of their formula, but they're able to produce hydroxide. Same idea here with something like sodium hydroxide in that solution. You pretty much got 100% these guys, and that means in that solution you got a ton of OH minus basically floating around freely in that solution, and that's going to decrease the amount of H plus, right? Increase the amount of OH minus, and the solution will be more basic. Weak bases, on the other hand, again, are weak electrolytes. So in this case, they'll actually accept the H plus coming that way. They're going to make us HF, a little OH minus. So although F minus does not have hydroxide in it, by doing this reaction, it's able to produce hydroxide, and that's why it's considered a base. Same thing here, is going to accept the H plus, and it will produce hydroxide over here, right, which will make it a base. This is also very commonly, as you can see, pretty much that weak base. You will always regenerate kind of the acid on the other side as a result of making that hydroxide as well. There is a relationship between an acid and its conjugate partner. So for example, conjugate base. So if you have a strong acid, its conjugate base will be relatively weak. And what that means, as we'll talk about in this chapter, is it will pretty much be sort of neutral. You can kind of think of it. It will not continue to react. So because it's relatively weak, it won't react. But if you have a weak acid, its conjugate base will be relatively strong. And what we will see in this chapter is if you do have that situation happening where you have a relatively strong conjugate base, it can continue to react and have an effect on the pH of the solution. So we'll actually see that. And same thing with our bases and the conjugate acid. It's that opposite relationship. So if you have a strong base, it's going to be a weak conjugate acid. And if you have a weak base, it will be a strong conjugate acid. So there is that, again, opposite relationship, which is really important, especially when we get into salts and hydrolysis reactions. It can have an effect on the pH of the solution, depending what type of sort of conjugate base is generated. Any questions on that there? Oh, here's a table from your book. And again, you can see the strong acids that we talked about. And again, those are pretty much the 6, and anything less than that will be kind of weak. Acid strength increases this way. Base strength increases this way. Again, they are opposite of each other. So strong acid, weak conjugate. Weak acid, strong conjugate going that way. Yeah, so again, opposite relationships that we see on the scale. So once again, I would focus on just those 6 and pretty much take a pretty good guess that, you know, anything else will be probably on the weak end. And same thing with the bases, you know, anything that is sodium, potassium, calcium, strontium, barium that has hydroxide, probably going to be strong. Everybody else might be on the weak side. So as we can see here with our strong acid, we expect 100% of it breaking apart. Our HF, again, we mostly have those guys still together in the solution. So that does affect the pH of a solution. So when you have a strong acid or a strong base, and you're asked to actually calculate the pH of that solution, you could do it because you know it will completely break apart. So in the case of a strong acid, when it breaks apart, you will always have H plus and some type of negative ion happening. And it is really the H plus in terms of its concentration that's really important for the pH, right? As we want to calculate the pH here. And same thing with our strong base. If you have a strong base, when it breaks apart 100%, you will have hydroxide and a positive ion in there as well. But it is the hydroxide that is the most important thing, because from the hydroxide, you can figure out the molarity of it, which means you could get the POH and then you could get to the pH, right? So when we have an actual formula given to us, which sometimes you do, so sometimes they may not just give you a generic H plus or OH minus concentration. They may say, hey, what is the pH of this, nitric acid solution? So if I had, say, 0.025 molar hydrochloric acid, and I want to figure out the pH. What I know about hydrochloric acid is it will break apart, as we've been talking about, into H plus and Cl minus. That means if this guy has a concentration of 0.025 molar, what is the concentration of H plus? It is. It's a 1-to-1 relationship, right? So this guy would be 0.025 molar. The Cl minus would also be, in this case, a 1-to-1 relationship, right? Which would be 0.025 molar. That is how molarity works, right? You base it on the coefficient and you multiply it. If you're not sure what I'm talking about, let me do the long version of that calculation just so we're clear. So, for example, if you had our 0.0205 moles per liter of HCl, we could do our mole to mole relationship, which is a 1 mole to 1 mole. So 1 mole of HCl gives me 1 mole of H plus. The moles cancel, and I end up with 0.0250 moles per liter of H plus. So that's the long version of that, but basically the short version is take the coefficient and multiply by the concentration, and you will get the correct concentration. Yeah. Any questions on that there? So in this case, that is all we would need to figure out our pH in my example. We could go into our pH equation here, 0.025. And let's see how I did with my made up number there, 0.0250. That's like a pH of 1.60, not too bad. There we go. And it is acidic, which is good because that's an acid, right? So those logical things you want to think about as well. You get an acidic pH for a base, maybe something went wrong in your reasoning, yes, or anything like that. Any questions on that? All right, so why don't you try a couple here, see what you get. Okay, let's take a look. So in this case, we could recognize this hopefully as a strong acid, which once again means that when it is in solution, it's going to 100% break apart into H plus and nitrate. And here we do have the concentration of 2 times 10 to the minus 3 molar. It is, in this case, obviously our H plus concentration that's important for our pH, and it is a 1-to-1 relationship, which means that the concentration of our H plus will be 2 times 10 to the minus 3. That means our pH in this case minus the log of 2 times 10 to the minus 3. Gonna get us some number there. 2 minus 3. There we go. That's going to be a 2.7 pH in this case. Yeah. First off, any questions on the calculation? 2.7 because this number has one significant figure, which means technically 1 decimal place in terms of our pH value, and that is acidic, which is good. Yes.
Is this case, is this universal, or there's some other cases where the coefficient for the products will be different and the molarity, but it's reverted to 1-to-1?
It's not universally 1-to-1. A lot of the strong acids, as we saw, there are monoprotic, as we saw, which means they have 1 H. So then they could only really give away 1 H in that case. So in terms of the acid, a lot of times the sort of concentration of the strong acid will be probably the H plus concentration, because most of the strong acids only have 1 H to give away, basically in the case. Yeah. Now, in the case here on the bottom, this is a strong base, right? It's got hydroxide. It's their group 2 towards the bottom. And that means that here we got a little barium hydroxide that's going to break apart here into a barium ion and a couple of hydroxide ions in this case. That means here 1.8 times 10 to the minus 2 molar. In this case, it is the hydroxide that's important to allow us to get to the pH. And in this case, it is a 1 to 2 relationship. So to get the proper concentration for our hydroxide, it would be 2 times 1.8 times 10 to the minus 2. And that would give us a hydroxide concentration here of 3.6 times 10 to the minus 2 molar. Remembering that this is the hydroxide concentration, that will allow us to go not into the pH at this point, but into the POH, which is minus the log of the OH minus, which would be 3.6 times 10 to the minus 2. And that will get us minus the log here of the answer. Looks like 144. And now we could get to the pH by basically taking 14 minus that number. And again, if by some chance you thought that was the pH, it should not make sense to you because that would be an acidic pH and this is a base. But when we do subtract it and get 12.56, that is a basic pH, which does make sense. So here, as to your question, probably more so on the base side, you might come across that where it's not going to be a 1-to-1 sort of relationship. But potentially, maybe something like sulfuric acid, you might have something like that as well. Other questions on that? So questions on pH, if you're given a strong acid or strong base, really just want to make sure you get the correct H plus or OH minus concentration, and then you could go into it. Any questions? So here again is that table from your book as well of those strong acids that we talked about, also really those strong bases kind of rolling from group 1 over to group 2. And then kind of coming down. So kind of go down, like I said, to potassium, make a right, and then go down again. Those are kind of your strong bases when they have hydroxide in them. So strong acids, strong bases, calculate pH. We do what we just did. But obviously weak acids, and as we'll talk about as well, weak bases will be a little bit different because they are weak acids or weak bases. They have the reversible arrows, which means they're going to set up an equilibrium. And that also means our favorite thing is going to be a ice table. It's going to be needed to solve for these things. So when we have to deal with weak acids or weak bases, we do have to sort of treat it like sort of an equilibrium problem. The good news is it's the same deal. But the difference is sort of what we're looking for at the end. So we can have a HA here, which in this example is just a generic weak acid. And we could write it with the water or again without the water here in our equation. And it's going to break apart with our reversible arrows here. We could write an equilibrium constant for this, which is again, same thing as we did previously, products over reactants. And if there are coefficients, again, they would be popped in there just like we did in the first chapter there with equilibrium. This is what's referred to as a Ka value as we add to our ever-growing list of Ks. So we got Kc, Kp, Kw, Ka. We're not even halfway there yet, but there's a lot more Ks to come. Again, this class is brought to you by the letter K in this case. So Ka, which is a weak acid ionization constant or weak acid equilibrium constant. The relationship is this: as the Ka value increases, the weak acid strength increases as well. And the reason for that is everything that we've talked about with equilibrium. So when I ask you, as the K value gets larger, do we have more reactants or products? Products, that's good, right? So more products. And the thing that makes something an acid, right, is the ability to produce free H plus in solution, which means if we have more products, we have more free H plus, which means that that will be a stronger weak acid. So when we're talking about Ka being larger and it being stronger, that's in comparison to other weak acids. It is obviously a lot weaker than any strong acid. So any strong acid will beat it. But if you want to compare between two, say, weak acids, you can use the Ka value, and the one that has the larger Ka value should be the stronger weak acid. If any of that made sense, I hope you have any questions on that there. So because this is, as I mentioned, a equilibrium, we do basically do an ice table with our acid. And we really would approach it the exact same way as we approached our ice tables in the equilibrium chapter, because it's still an equilibrium. So we do our ice table. The only main difference is in a lot of these cases is the additional step of once you get your X value here, in a lot of cases, that's your H plus, then you need to calculate the pH. So unlike in, say, an equilibrium problem where maybe interested in every base concentration at equilibrium or every base pressures at equilibrium, a lot of times in these problems, we're just really kind of interested in what the pH of the solution is or the weak acid is. So, and in a lot of cases, when you do solve for X in your table, that will be equal to the H plus concentration, which means then you could take it and go into the pH formula and calculate the pH of it. So it works very similar to it. You may have to look up some Ka values in tables. This is a table from your book. And I think we talked about it as well, that these H pluses do come off one at a time. So you can potentially have 3 different K values that you find in this table. Like what we see here, this is sometimes referred to as the Ka1, Ka2, and Ka3 value, as one for each hydrogen that comes off. Similar here, phosphoric acid should be in here somewhere, I think. There it is. So something like phosphoric acid has these 3 hydrogens that will come off basically one at a time. And that's what each of these 3 equations represent, or values represent. So for example, here, the first thing that would happen would be H3PO4 would lose 1 H plus, and you'll be left with H2PO4 minus, and this would be the Ka1 value, which in this case would be this guy here. Then what would happen is the H2PO4 minus will dump off the next H plus and be left with HPO4 2 minus. And that would be your Ka2 value that you would find in this table for basically the second hydrogen coming off. And lastly, the third hydrogen would come off at this point. The HPO4 2 minus will lose 1 more H plus and make PO4 3 minus, which would be the Ka3 value here, right? We'll talk a little bit more about this later on in this chapter, but when we look at these numbers between the Ka1, Ka2, Ka3, it tells us which one should be easier to take off and which one should be harder. Which one is the hardest to take off? First one, second, or third? Do we know how to use that number to help us decide that? The hardest one to take off is actually the last one, yeah? And we see that by the equilibrium value constants. Very first H that comes off, that's a large value compared to the other, or smaller? That is the largest of them all, right? Which means in that case, you have mainly products, right? Which means we got those guys come off. Now we get to the second one, it now has a negative charge, right? And you're trying to rip off something that's positive, right? So it's going to hold it tighter. So we see that the K value actually goes down, which means not as much products, right, being made. So less H plus is going to come off in the second time around. And when we get to the third one, it's even smaller, right? A lot smaller than the second one or the first one, which means not a lot of products coming off in the end, not a lot of H plus coming off. So what we'll see here, and what you typically see, is it's a lot easier to remove the first one for that neutral guy, and then it gets increasingly harder to remove further H pluses along the way because really the opposites attract. It kind of holds it a little bit tighter as well. So again, that's why you might see multiple K values in this table. And again, it represents basically each of the hydrogens coming off at a time. When you have something that's a diprotic acid or a polyprotic acid, triprotic acid that has 3 of them. All right, so as I mentioned, it's pretty much the same procedure. So go for it here. What is the pH of this solution? 0.5 molar hydrofluoric acid solution, Ka value, 6.4 times 10 to the minus. Okay, let's take a look, see how you're doing. So a couple of things we want to look at when we sort of read this question is we have 0.5 molar hydrofluoric acid. So first off, I know this is a weak acid because there is a Ka value, right? So will strong acids have a Ka value? They will not, because they 100% break apart into ions, which means there's no equilibrium, right? So no equilibrium constant, which means that's a pretty big hint. Yes, that if you see a Ka value given to you, or if you could find it on obviously a Ka table, that is definitely a weak acid. So these are things that we don't want to overlook when we're sort of looking at the problem. That also should then tell you it's a weak acid, it's an equilibrium. I should be doing like an ice table here. Yeah. So these are things we want to think about. So in order to do an ice table, we do need a little equation of what's going on. So here you could have your HF, which will have the two arrows breaking apart into H plus and F minus. And once again, in this case, if you do want to include the water in the equation, it's okay. The only difference is you'll get H3O plus on the other side, which is the same thing. So if you want to include the water, you can. As I mentioned earlier, I think mostly do not include the water with acids. So, but if you do, you can. That also means we could write our Ka expression, which would be the concentration of H plus, concentration F minus, divided by the concentration of HF in this case, and it equals our number up here. So we're going to approach this the exact same way as a normalized table. So initially, really the only thing given to us is 0.5 molar of this guy. We have nothing given to us in terms of the other concentrations. So once again, since we have zeros on our product side, it's pretty safe to assume that it is going to head in that direction, which tells us our minuses should be on the left, right, and our pluses should be on the right. So this is going to be minus x plus x plus x, which means when we get to equilibrium here, we will have 0.5 minus x, x, and x. Any questions on the ice table here? Yeah. Now that we have our ice table set up, just like before, we're going to take our equilibrium line here and basically put it into our expression. That's going to give me x squared. I'm going to spit that out, maybe 0.5 minus x, and that will equal our 6.4 times 10 to the minus 4. At this point, we want to solve it. And when I look at that K value, is it a large value or a small value? It is small, which means when I have a small value of K, I can do what? I can make an assumption that X is equal to 0, which again means you don't have to always do the quadratic. Yes. So you might want to try that here. So we will try and assume that X is equal to 0 as we have a small K value, right? Like we talked about it in the previous chapter. So doing that, a reminder that the x that we're going to get rid of is any x that we're going to basically subtract from or add to a number. That would make this then x squared divided by 0.5 is equal to 6.4 times 10 to the minus 4. We're going to multiply to the other side and then do a little square root action afterwards. And if you do that, 6.4 exponent minus 4 times 0.5, we're going to then take the square root of it, and that will give us an x value here of 1.7889 times 10 to the minus 2. First off, any questions on the assumption there? The other thing that we talked about with the assumption is if you do make it, you also need to check it, right? So you should always check your assumption. We are following the 5% rule in this class, which means that you take the x value and you basically divide it by what you're going to subtract it from. So if I do that, I'm going to take that x value, I'm going to divide it by 0.5, times it by 100%. And if it is 5% or less, you're in good shape, which I think in this case, that's a 3.58%. That is a good deal. Yes. So the check is good in this case. Any questions on that there? Now, if I did this and it was over 5%, what would it mean? I need to go back in, solve it, probably with the quadratic. Yeah. So again, if it's over 5%, you got to go back and solve it some other way. If it's less than, you put a happy face and continue on with your life. Yes. So really, as we talked about in this case, we're interested in the pH, which really the only thing that's really of interest for us in this problem in the ice table is really H plus. which we can see here that is the X value. And that means that this X value also equals our H plus concentration. And in this case, then we could go into our pH minus the log of, too much light here, 1.7889 times 10 to the minus 2. That's going to give me a pH in this case of, we'll call it 1.74, I think, give or take as well. Yeah. Any questions on any of those steps there? So, think about if you can solve it some other way, it might be a little bit easier in a lot of cases. But again, if you did the quadratic root, you should really end up with the same answer as well. So you can still do the quadratic if you want to. This also makes sense. This is an acidic pH. This is an acid. So that's all good. Yeah. Any questions on any of that? All right. So as we talked about, you definitely do want to check it. So for example, if we had really the same problem here, and we basically went through the same ice table as we just did. We would have initially here 0.0500. Change would be minus X plus X plus X. Really, the only thing changes our initial concentration here. That's going to give us our X squared over 0.05 minus X equals 6.4 times 10 to the minus 4, I think, right? Now, if we make our assumption and assume X is equal to 0 in this case, we're going to get 0.05 times 6.4 to the minus 4. We're going to take the square root of it. And if we solve it the same way, multiply and then take the square root, we'll get an X value of 5.657 times 10 to the minus 3. Now, when we take this and divide it by our initial concentration and times it by 100%, and we're looking now in this case like 11.31%, right? Which is not so good. Yeah. So sometimes people get into the habit of thinking the assumption will work in all times, but you should always check it to make sure. In this case, it will not work. So we would have to go back again and sort of solve it some other way. The reason it doesn't work in this case, it has to do with the initial concentration, right? Our other guy was 0.5 molar, right? Which is much larger, like 10-fold larger. All right. So when you have a larger concentration of your acid and a little bit of it comes off, that's not such a big deal. But if you have a smaller concentration of your acid, everybody okay? Yes? Okay. If you have a smaller concentration of your acid to begin with, and you take a little off, it is much more important than being negligible. I related to pizza, right? You got a whole pizza, you take one piece, not a big deal. But when there's only 2 pieces left, and somebody takes a piece, much bigger deal, right? So the initial amount that you start with is really important here, because even a little bit that comes off is a big deal. And that's why when we have our zeros here and our X squared, we don't get rid of the X squared because it started at 0, right? So whatever it makes is pretty significant. I got it by the same way we did before. We would assume that X is equal to 0. Then you would get X squared divided by 0.05 is equal to 6.4 times 10 to the minus 4. You're going to multiply, and then you're going to take the square root afterwards, yeah? You multiply 0.05 times 6.4 times 10 to the minus 4, so 0.05 times 6.4 to the minus 4. That gets you basically X squared is equal to 3.2 times 10 to the minus 5. Then you're going to do a little square root of both of them, yeah? And then you get there. Other questions on that? Okay. So make sure you always check it. In a lot of cases, it will work, but it will not necessarily always work. Other questions on that? So as we see here, when we are dealing with weak acid problems, we basically approach them the exact same way. as equilibrium problems. But again, we're oftentimes interested in just the H plus so that we can calculate the pH. We will, as it says here, ignore any OH minus or H plus that comes from water. We will determine it strictly from the acid. And what I mean by that is there are some problems, and some books will go, well, your H plus concentration is much less than just the stagnant H plus concentration from water, and they'll take that into account. So to make it simple, we're not going to do that. So basically all of the H plus that comes into that solution is going to come from the weak acid, and that's how we're going to calculate the pH from it. And same thing with the base. All the OH minus that comes into the solution would come from the base. So we were not going to worry about water's influence on the H plus or OH minus concentration. All right. So we will obviously calculate the Ka and get this species and calculate the pH. We know we should be using a Ka because what do we see on the product side? Yeah, so that's also sometimes important. People sometimes not knowing what K value you should use. So if you write the equation correctly, which is why it's important to make sure you know how to write these equations, and you see H plus or H3O plus on the product side, and you're doing some type of equilibrium calculation, Ka value is what you should use. Just like as we will see, you should use a base sort of equilibrium if you see OH minus on the product side. And sometimes you will have the wrong K value given to you, and you got to know, okay, I need to use the correct value in this case. So that is how those two things are related to each other. You got H plus, H3O plus on the product side, should be using the Ka value for your calculation. Let's try another one here. What is the pH of a 0.122 monoprotic acid that is 5.7 times 10 to the minus 4 Ka value? Let's see how you're doing. It's getting towards the end here. Once again, we know a couple of things when we look at this problem. We see go that way. We see a Ka value, so this is definitely a weak acid. So again, we should be doing some type of ice table in this case. Since they really didn't give us anybody specific, I could always use kind of HA as just a generic sort of formula for an acid. And when this would break apart, we would have H plus and a minus in this case. You know, similar to HCl gives you H plus and Cl minus as well. We could write our Ka expression, which we will need as well, which will be our products divided by our reactants in this case. And again, that will equal our 5.7 times 10 to the minus 4 there. Let's write it here. Run out of room. We're going to do our ice table. So we're given 0.122. Once again, we were not given any of these guys, which means it should be heading in the right direction there towards the products. So our minus and pluses will look something like this. And then at equilibrium here, we'll bring everybody down and not forget the 1 as well. Our X and our X. Any questions on the ice table here? So now we're going to take our equilibrium line and put it into our expression. That's going to give us our X squared divided by 0.122 minus X is equal to 5.7 times 10 to the minus 4. We could assume X is equal to 0 here as our K value is small. Good or bad? If you didn't check, it's actually bad. It's like 6-ish% or so, yes, which means not so good. So that means we do need to go back and solve it some other way so we don't have an unhappy face when we do it, right? So we're going to multiply everything here to the other side, and that will give us X squared is equal to 6.95 times 10 to the minus 5 minus our 5.7 times 10 to the minus 4x. We're going to bring everybody to the same side to get it into our quadratic. So that's going to be X squared plus 5.7 times 10 to the minus 4x minus 6.95 times 10 to the minus 5 equals 0. Again, I'm just bringing everybody on this side back over to the other side. That's going to give us our A, B, and C, right, for our quadratic when we go into it. And in this case, that will get us x is equal to minus b, which is minus 5.7 times 10 to the minus 4, plus or minus the square root of b squared minus 4ac. If you put all the numbers in and do that part of it, it is 0.000278325. And then if you take the square root of it, 0.0167 is what you get out of it. And again, that is obviously our inside there, b squared minus 4ac, right? And that's minus b plus or minus 2 over a, right? That means us 2 over a on the bottom, which is 2 times 1, which is 2 in this case here. So that's going to give us our two x values in this case, which is doing negative and positive. So doing the positive here, or adding, I guess is the way of saying that, we would get an x value of 0.008065. And doing the subtraction, going the other way, gives us an x value of minus 0.008635. Any questions on that there? At this point, we are obviously interested in our H plus concentration so that we can calculate the pH. So clearly, which one should not work? Yeah, the negative. We can't have a negative concentration. So this should be our correct X value, which means that that is also going to be our H plus value there from our ice table. As we can see, that is what it equals at equilibrium. That means we're ready to go into our pH. So our pH here will be negative of the log of our H plus 0.008065. Gonna give us a pH of about 2.09, I think. Yeah. This case. Any questions on any of those steps? So once again, you do want to make sure you check. Yeah. Yeah, so when you do the quadratic, just like we talked about in the last chapter, it is possible to get two positives or two negatives even, and a positive and negative. But the major difference would be when you go back into the equilibrium line, one of those positive values will get you a negative value when you actually solve for it. So as I mentioned before, it is possible to get the two positives, but it should lead you to one negative when you put it back in. Just like sometimes people think maybe there's something wrong if they end up in a rare case that you could get two negatives, but one of them will actually give you a positive number when you put it back in. So it will actually work out okay. So those are really your options. Other questions on that there? Yes. I probably do. The correct one here probably would be based off of that concentration, where it has 3. So it probably should have 3 decimal places.